Code for QuickSort. Last time we analyzed QuickSort and we looked at the best case and the worst case. So what was the best case? What is the best case? What was the case? Yeah.
Both sides of the pivot were even.
Yeah, so perfectly balanced. Okay, perfectly balanced input. So best case is perfectly balanced. Perfectly balanced at all levels. And in that case, we got a recurrence of T of n equals 2T of n over 2 plus Cn. And the solution for that was theta of n log n. Just similar to merge sort. And the difference between QuickSort and merge sort in this case is where? Yeah, the difference is where this Cn is coming from. In merge sort, it comes from combine. And in QuickSort, it comes from divide, which is the partition. And the worst case, we looked at the worst case, which is least balanced. Of course, we are referring to the partitioning. So perfectly balanced partitioning. And this is least balanced partitioning. At all levels. Okay. So when it's least balanced, we said that we will get something like this, n minus 1, and so forth. Now, what should the input look like in order to give us this least balanced partitioning at all levels? What kind of input will give us this?
Sorted.
Yeah, so if the input is sorted, if you look at this, if you have 1, 2, 3, 4, 5, 6, then if you pick the pivot as the last element, which is what we have been doing so far, but we will talk about changing this today, we will see that it's not a good idea to pick the last element as the pivot. So 1, 2, 3, 4, 5, 6. So it will get partitioned like this. 1, 2, 3, 4, 5. Then we pick 5 as the pivot. Then it's going to be 1, 2, 3, 4, and so forth. So if the input is already sorted, we will get this. Okay, so sorted input will not always be a best case in a sorting algorithm. So this is an example of a sorting algorithm where sorted input is the worst case. Now, we analyzed this last time and we concluded that T of n in this case equals theta of n squared. So that was the last thing that we did last time, concluding that it's theta of n squared. But theta of n squared in sorting is as bad as it can get. So the worst sorting algorithms like insertion sort, selection sort, bubble sort, they're n squared. It can't be any worse than n squared. You know, unless someone comes up with an algorithm that doesn't make any sense and does every operation many, many times and repeats and has lots of redundancies and all of that. But n squared is as bad as it can get. However, QuickSort is one of the most widely used sorting algorithms in practice. And it's indeed quick. So in practice, it's called QuickSort, but it's indeed quick in practice. So how does this, do we have a contradiction here? How do we reconcile this popularity and success of QuickSort in practice with this worst case running time of n squared. How do we reconcile? Yes?
You can choose a randomly generated pivot point rather than always selecting the same one.
Okay. Well, if we pick the pivot at random instead of selecting the last element, how will this help?
You're much less likely to get n squared. It's practically impossible.
Okay. So yes, selecting the pivot at random will make this worst case extremely unlikely. How unlikely? Can you quantify this? Unlikely. Can you quantify the probability of getting this? Yes?
1 over n?
Well, 1 over n is the probability of getting this bad partitioning at level 0.
Wouldn't it be 1 over n times 1 over n or something like that?
Well, this is 1 over n, but at level 1,
1 over n again. 1 over n minus 1.
yeah, it's 1 over n minus 1, and these are independent
1 over n
events.
factorial.
Yeah, so it's, in order to get this worst case, the probability of picking the worst possible element, or the maximum or the minimum to be the pivot, is 1 over n. Well, in fact, the probability of picking the maximum is 1 over n if the elements are distinct. And the probability of picking the minimum, which is also another worst case, is 1 over n if the elements are distinct. So let's just look at this probability of picking the maximum element if the elements are distinct. At this level, it's 1 over n. At the next level, it's 1 over n minus 1. At the level after that, it's 1 over n minus 2, and so forth. So this is like 1 over n factorial. And if n is a large number, well, if n is a small number, then nothing matters. You can use any algorithm. Remember this: if n is small enough, then you can use any algorithm, and all algorithms are going to be fast. Even exponential or even factorial, if n is small enough, they're going to run fast. So in this case, for n squared, you can go up to 1,000 or even 10,000, and you still, the algorithm will still complete within a fraction of a second. However, if n is large, this means that this probability here is what? Yeah, is practically 0. So this probability will tend to 0 when n gets larger. Yeah, so that's why this worst case is very rare in practice, or it's unexpected in practice. It's the practical probability is 0. Now, encountering this worst case, exactly this worst case is unlikely, but sometimes QuickSort will run into some cases where the number of levels is fairly large. Remember the numbers from last time here. We had for n equals a million. Here we have 20 levels because we have log n levels, which is 20 levels. Here we have a million levels. So the worst case is a million levels, which we said that this is likely to lead to stack overflow. Here we have 20 levels. So in practice, if this gets to 30 levels or 40 levels or 50 levels, it's not going to be a big problem. It will still be in the order of log n, right? It's not going to be in the order of a million. It's not order n. It's going to still be order of log n. Okay, so this worst case is rare, but we will see in a minute that even bad cases are not likely. So worst case is a million, best case is 20 million. What we would expect in practice is 30, 40, 50, something like that, but not, for example, thousands. thousands of levels is unlikely. Now, before we explain this further, we explain why bad cases or having too many levels is unlikely. Before we do that, let's emphasize the advantage of QuickSort. So, in order for QuickSort to be successful in practice, right, it has to have an advantage over other algorithms. And in this course, we have covered merge sort. So what's the advantage? Yeah.
Merge sort takes up more memory because you're creating more arrays.
Yes, it takes more memory because of that temporary storage, those temporary arrays. So these temporary arrays, they do not only take up more memory, they also take more time because you want to copy to these arrays. So copying to these arrays takes time. So it's lots of memory operations. And in fact, if you look at the, we don't have the code for the partitioning, but if you, we wrote it last time. If you compare the code for the QuickSort partitioning with the code for merge sorts combine or merge, you will see that merge sort does a lot more work than QuickSort. So the loop for QuickSort is very small, and it basically does one compare and one possible swap. So if the element is smaller than the pivot, it's going to swap, and that's all. Okay, that's all what it does. So the hidden constant in QuickSort, the hidden constant in QuickSort is smaller. So what do we mean by the hidden constant? What do we mean by the hidden constant here? Where is it hidden? So there is a hidden constant that is smaller in QuickSort than it is in merge sort. Yes?
The constant of the loop, how much you have to do within the innermost loop.
Yes, yes, but why am I using hidden? Why am I using the word hidden here? Because both of them are asymptotically n log n. So it's hidden in the asymptotic notation. So in the best case, QuickSort and merge sort, both of them are theta of n log n. If QuickSort is in its best case or close to its best case, and merge sort. So in merge sort's best case, it's n log n. But there is a hidden constant that is not visible in the asymptotic complexity. Because if you just look at the asymptotic complexity, you would think that merge sort is better because merge sort is always n log n, while QuickSort may be something greater than n log n. So it may, by looking at the asymptotic complexity, it will look like merge sort is better. But there is a hidden constant in the asymptotic notation, which is how much work we do. And that's in favor of QuickSort. Okay. Now we will say more about the probability of the worst case or the probability of bad cases in QuickSort. So in order to understand this, we will first analyze an interesting case for QuickSort that looks extremely unbalanced. So we will analyze an extremely unbalanced case of QuickSort and see what the asymptotic complexity is in that case. So that special case or unbalanced case is the following. What if we start with an array of size n, then we divide this into n over 10 and n over 10 and 9n over 10. So 1/10 and 9/10. Of course, here we are ignoring what? We are ignoring the pivot. Right? So for a large n, because these cannot, the sum of these will be exactly n. But in reality, it's the sum of the sizes of the two partitions is going to be n minus 1 because of the pivot here. Okay, but we are ignoring the pivot because it's much smaller than n, because we are analyzing this for large n. So now what if we keep doing this? So now we split this into n over 100 and 9n over 100 and so on. So if we do this kind of splitting, so assuming that the partitioning will be at all levels 1/10 and 9/10. Of course, is this a practical assumption? How likely will it be to have this split in practice? Is it likely or unlikely? Why is it unlikely? It's always unlikely to have the same split at all levels.
1
Yeah.
10 times 1 and 10 times 1 and 10.
Yeah, so it's unlikely to have the same split at all levels. But we are studying this because it's as an idealized case that we can analyze. Because if the split is going to be different at each level, that's a hard case to analyze. So we are assuming that at each level, the split will be unbalanced, and that the same split will happen at all levels in order to simplify the analysis, in order to make this easy to analyze. But the point here is that this is not a best case. This is not the way we would like it to be split. It's a case that looks bad. And if the result of this turns out to be good, then what we expect to see in practice is going to be better or worse than this?
Better.
Better, yeah. So this is too bad to happen in practice. So let's analyze this. So the analysis is going to be a good practice of the recursion tree method. And in this case, if we write the recurrence, we will see that we cannot apply the master theorem, because here T of n equals what? T of n, we are dividing T of n into T of n over 8 over 10 and T of n over 9n over 10. So this is the split. We are dividing it into n over 10 and 9n over 10 plus Cn. Cn is still the partitioning time, still Cn. Now this is the recurrence. Can we use the master theorem for this recurrence? No, we cannot, because this is not the form that we can apply. This is not a form that we can apply the master theorem to, because here we have two terms with ratios. The form that we applied the master theorem to has only one ratio, not two ratios. Okay, so we cannot apply the master theorem to this. So we'll have to do the recursion tree, and the recursion tree for this. Now, who has done enough practice with the recursion tree to tell us what to do? So at level 0, what will we have? Cn. So at level 0, Cn. At level 1, first question, how many branches? Two branches. First branch is Cn by 10. Second branch, 9Cn by 10. Then at the next level, we'll have two branches. This is going to be what? Cn by 100. And this 9Cn by 100. And this is going to be 9Cn. Yeah, we divide by 10. And this, yeah, so this is going to be 9 times this, which is 81 Cn by 10. Okay? Well, and we keep dividing.
Shouldn't it be over 100?
9 Cn by 100.
Yeah, it's 100. Yeah. Yes, you are right. So, yeah, we are dividing. First, you divide this by 10. And this is divided by 10, and you multiply by 9. Yeah, so it's over 100. And in the next level, it's going to be over 1,000. OK. So now if we try to add these at each level, so this is level 1, this is level 2, this is level 2. At level 0, we have Cn. At level 1, we have Cn over 10. So this is 10 Cn over 10, which is Cn. And at this level, it's going to be 81 plus 9, that's 90, plus 90, 99 plus 1 is 100. Cn divided by 100. And that's Cn. So we will get Cn at all levels. But now the question is, will we continue to get Cn at all levels?
Yes.
Will we continue to get this at all levels?
Yes.
OK, so the answer is no. Why? Why is it no?
Unbalanced.
Unbalanced. So what does this mean?
Partitions will not be equal at every level.
So what will happen?
Some will end off because it can't be divided.
Yeah, exactly. Exactly. That's the point. Some of them will just reach the base case, which is 1. So which one will reach the base case sooner? The leftmost or the rightmost? Leftmost, because this is going by 10. So this is dividing by 10. So this is going to get to 1 sooner. So at some point, this will get to 1. So it will reach its base. But those will continue. So even after this point, those will continue. Right? Because this is going, the division is happening slower. So here we are dividing by 10. Here we are dividing by what? We are dividing by 10 over 9. We are dividing by 10 over 9, which is 1.1 roughly. So we are dividing by 1.1. Here we are dividing by 10. So this is going to get to 1 sooner. Now, given this, so as long as all of them are there, we will get Cn. Well, let's say before the base. As long as all of them are there, we'll get Cn. Then after one of them disappears, what will the value be? What can we see about the sum of costs at those levels after this level, when this reaches its base case? Will the value be Cn less than Cn or greater than Cn? Greater?
Less.
Yeah, it's going to be less. Something will disappear. So something here, you'll have something that will go away, and this will just continue. This with a full tree, with a complete tree, we are getting Cn. After a certain point, a certain level, when this reaches its base, so this is going to disappear, and those will continue. Right? So what we will be getting at subsequent levels is something less than or equal to Cn. Less than or equal to Cn. OK? Now, what does this mean? Of course, the base is not going to be different, right? The base is going to be still, the base is going to be how n leaves, and it's going to be theta of n.
Yep.
But with the internal cost here, what can we say about the internal cost?
The height's going to change.
OK, that's good. The height is going to change. Is it going to be larger or smaller than the height of merge sort?
Larger.
Larger, because here we are dividing by this small ratio, which is 1.1. So the maximum number of levels, if we look at this, so number of levels or let's say maximum number of levels, because it's not going to be a complete tree. Some of them will continue all the way to the maximum, and some of them will end here. But the maximum is going to be log n base.
9/10.
Yeah, exactly. Log n base, the small base. Yeah, log n base 10/9. Okay? Log n base 10/9 is a much larger number than log n base. So here this will end at log n base 10. But this is going to be log n base 10/9. So what does this mean? It means that if the partitioning is unbalanced, but we're still dividing by a ratio, still the division is happening by a fixed ratio, and the ratio is the same at all levels, the number of levels will still be logarithmic, but to a smaller base, which means that it will give us a larger number of levels, still logarithmic in order. So when you take the logarithm for a small base, you will get a larger number, but it's not going to be much larger, right? Because all logarithms are of the same order anyway. So now, what can we say about the cost, the internal cost here? Can we use theta? Can we use the theta notation here, or we have to use big O?
Theta.
Theta? But in order to use theta, you have to have an exact analysis. And here we're not doing exact analysis. We're only bounding this. We're only saying that this is not going to exceed Cn, but we didn't say what exactly it is. So we are bounding it. We're not computing the exact value. So because we are bounding this, we can only say that the internal cost is going to be O of n log n. We can't say theta here. Based on this analysis, we cannot use theta. We can only use big O because we are computing an upper bound. So we can say that the actual asymptotic complexity, based on this analysis, will be n log n or smaller. Of course, it's not going to be smaller. Of course, it will not be smaller than n log n, because we know that even with a perfectly balanced partitioning, it's n log n. But based on this analysis by itself, we cannot use theta. We should use big O. OK. So in conclusion, what does it mean? It means that even with this partitioning that looks unbalanced and ugly, we will still have an n log n behavior. N log n with a smaller base, which means a larger number of levels. So it will be a measurable difference in the actual running time. So in the actual running time, for this is going to be much worse than the actual running time for n log n, but still of the same order as n log n, so it will not be as bad as n squared. As you will see when you do assignment 3, for n squared, if n is 1,000,000, when n equals 1,000,000, well, you will see how long it will take. So, well, you should do some calculations, but when you run this n squared for 10 equals 1,000,000, you will see how long that will take. It's going to take hours. But any n log n is not going to take hours. It will be slower. Maybe it will take seconds, but not hours. So this is what the asymptotic complexity means. OK? So now, so this is what this analysis leads to. Now if we think about the behavior of QuickSort on average, now we have analyzed this case where the ratio is the same at all levels. But in reality, the ratio is not going to be the same at all levels. So in reality, we expect something like we start with this, then maybe we get unlucky at level 0, so we'll have a bad partitioning like this. But on average, we can't be unlucky at all levels. So if we get unlucky at this level and the partitioning is bad, then we are likely to get lucky at the next level and get a good partitioning like this. So if you think about this, if you think about the behavior of QuickSort, if you get a bad partitioning at one level followed by a good partitioning at the next level, alternation of good and bad, how bad this can be. So this is good, then you will get a bad partitioning at this level. And so for this, and now you have this. So you get a mix of good and bad. Now if we keep alternating between good and bad, how much difference will this make relative to getting good partitionings at all levels? What's the factor here?
None. It's going to be more. It's going to be good and bad. It's going to even out.
Well, well, the number of levels is like double. You can think of the bad partitioning as a level at which you are not making progress. It's just like you are wasting one level. Then at the next level you will catch up and you will do a good partitioning and you will make progress like you do in the best case or with merge sort. So you can think of this as a bad partitioning is wasting a level. So this is wasted. This is making progress. This is wasted. This is making progress. Wasted, making progress. So it's like doubling the number of levels. Right, so if you really get a mix of good and bad, you will be simply doubling the number of levels. So the number of levels is going to be 40 instead of 20. And that's not nearly as bad as a million.
This is a constant.
Yeah, but here we're not doing an exact analysis for a specific case. Here we're trying to intuitively think about the behavior of QuickSort in practice with a mix of lucky and unlucky partitionings. Okay, because in practice it's a mix of lucky and unlucky things. Like in real life, there is always a mix of lucky things happen and unlucky things, and this is life. You can't get unlucky things all the time and lucky things all the time. It's usually life is a mix. Life is balanced. Okay, so that's why we expect. So this is basically an intuitive argument. It's an informal. This is not mathematical. This is an informal argument that on average, we expect QuickSort to be n log n. So this argument says that on average, QuickSort is O of n log n. Okay, and what helps with this is randomizing the partition, randomizing the pivot, of course. And to randomize the pivot, it's very easy. So instead of partitioning, you do randomized partition. And in randomized partition, what you do is the following. So this is your array. You pick the pivot at random. So you pick one of these at random. Maybe it's this element. And then you swap it with this. you swap it with the last element, then you proceed as we did in previous lectures. So you still proceed with the last element, but before you do that, you pick the last element at random. So pick one of the elements at random, you swap it with the last, and then you proceed the way we did in previous lectures. So the way you implement this is that you say, let's call it y equals random between p and r. So get a random number between p and r. This is p, this is r. So it gets you an index between p and r. Then you do swapping between a of y and a of what?
R.
A of r. So this is y, and this is r, and you swap them. And then a randomly selected element will be in the last, at the last index in the array. Okay? Yeah.
Is there a cost for the random function?
Well, yeah, that's a good question. So in fact, yeah, when we analyze, we should account for the cost of for the cost of any function that we call, and here we will assume that it's fast enough because it's based on lookup tables. But this is a very good point. Yeah, so we will assume that it's fast enough. But that's a good question, an excellent question, because in algorithm analysis we have to account for everything, and everything that we put in there we have to think about its computational cost. Yeah, but we will assume that it's a fast function because it's based on table lookup. It's not gonna be doing, if it does an n squared algorithm internally, of course that's gonna kill the whole thing. But we'll assume that it's quite fast. We will assume that it's to a very good approximation. It's a constant time algorithm, and you will